Welcome to the Deep Dive. You, the learner, have sent us these excerpts from the Go programming language book.
That's right.
And our mission today is pretty straightforward.
Yeah.
We want to extract the core philosophy, the really interesting bits about what makes Go tick.
Get the essence of it.
Exactly. Get
Yeah.
the essence without wading through every single detail. So let's start at the beginning. Where did this language even come from?
Right. So it has a surprisingly recent history, actually. Go was born at Google.
Google. Okay.
Yeah, back in September 2007. The creators were Robert Griesmer, Rob Pike, and Ken Thompson.
Wow, those are some pretty big names, Pike and Thompson especially.
Absolutely. Legends, really. And they announced it publicly November 2009. So it's definitely a language built with a modern perspective.
Modern perspective. What does that mean exactly? What were they trying to, achieve with Go?
Well, their goals were ambitious, but also really practical.
Then,
They wanted a language that's expressive, easy to read and write. Also, one that compiles and runs super fast. Blazingly fast, as the book says.
uh-huh.
And crucially effective for building reliable, rock-solid programs, the kind of stuff Google itself needs.
Right, systems that just work. Now, you often hear Go described as like a C-like language, or maybe C for the 21st century.
Yeah, that comes up a lot.
If someone listening knows C, what should they take away from that comparison?
It's a decent starting point. Go definitely borrows some basics from C.
Like what?
Think syntax, how you write expressions, control flow, like if and for loops, basic data types, integers, floats, that kind of thing.
Okay.
It also took C's call-by-value approach for function arguments. And importantly, it has pointers.
Pointers, right. Direct memory access.
Some direct control, yeah. Like C, Go aims for efficient machine code that works closely with the OS. It feels familiar in that way.
But it wasn't just C, was it? The book mentions other influences too.
Precisely. It wasn't just a C reboot. They also looked at Nicholas Worth's languages.
Like Pascal.
Pascal, Modula 2, Oberon.
Okay.
Yeah. From Modula 2, they got the idea of packages organizing code into reusable chunks.
Uh-huh. Packages.
Oberon simplified that, and Oberon 2 specifically influenced Go's syntax for declaring packages, importing them, and how you define methods.
Methods. Okay. We'll get to those later, I
And
assume.
functions tied to types.
So it sounds like they sort of cherry-picked ideas.
Yeah.
But the book also mentions this cultural agenda of radical simplicity. What's that about?
That's really key to understanding Go. It's core to its identity. The designers consciously aimed for a minimal set of features.
Minimalist.
Yeah, very much so. They wanted features that worked cleanly together. Being relatively new, they could learn from other languages' mistakes, maybe.
Avoid the cruft.
Exactly.
Yeah.
Focus on doing a few core things exceptionally well, like garbage collection automatic memory management. That's huge.
No more malloc and free all the time.
Right. A really solid package system. First-class functions are just like data, clear rules for scope, a clean system call interface, and built-in immutable UTF-8 strings for text.
Okay, so those are the things Go does have and does well.
Yeah.
But the book makes a big point about features Go deliberately lacks.
Absolutely. What's not in Go is almost as important.
Like what specifically?
Okay, so no implicit numeric conversions. You have to explicitly say, in my float.
Explicit, okay.
No constructors or destructors like in C++ or Java. No operator overloading plus is always addition or string concatenation. Nothing else.
Keeps things predictable.
Very. No default parameters for functions. No traditional inheritance like in O languages.
No classes.
Not in the typical sense, no. Generics were missing for a long time, though they've been added recently.
Oh, okay.
No exceptions for error handling. We'll talk about Go's error values later. No macros. No function annotations. No thread local storage built in.
Wow, that is a significant list. So this radical simplicity, what's the payoff? Why leave all that out?
Well, the argument is stability. By keeping the language lean, it's more stable,
Easier to maintain.
easier to maintain, and crucially, it ensures really strong backwards compatibility.
Ah, so old code doesn't break with new versions.
Pretty much. Code written for Go 1.5 will almost certainly compile and run fine with Go 1.2, say. That's a huge deal for long-term projects. Less churn, less breakage.
Yeah, I can see the appeal. Now, the book also talks about Go being designed with modern computers in mind. How does that show up?
Right. It encourages you to think about how modern hardware works, especially memory locality, keeping related data close together in memory.
Why is that important?
Performance. Accessing memory that's close by is much faster. Go's built-in types and library structures are designed to work naturally without lots of hidden setup or memory allocations.
Fewer hidden costs.
Exactly. And when you use Go's aggregate types, structs, and arrays,
Structs like records, arrays like lists.
sort of, yeah. The elements are stored directly, contiguously in memory, not like some languages where fields might be pointers to other memory locations.
So less jumping around in memory.
Right. It means less storage overall, fewer separate memory allocations to manage, fewer pointer indirections, faster access.
Makes sense. And modern computers are parallel too.
Yep. And Go has concurrency baked right in from the start, using a model called Communicating Sequential Processes, or CSP.
CSP. And that relates to those lightweight Go routines I've heard about.
Yes. Goroutines are functions that can run concurrently. They're incredibly lightweight compared to OS threads.
How lightweight?
They start with tiny stacks, just a few kilobytes that can grow and shrink as needed. So it's practical to launch thousands, even millions of them.
Millions. Wow. Okay.
Yeah, the book suggests 1 million might be feasible for some things.
Okay. That gives us the big picture: simplicity, efficiency, concurrency. The book then has a tutorial in chapter 1. For someone new, what's the gist of that?
The tutorial aims to get you doing useful stuff quickly, like real-world tasks, not just abstract exercises.
What kind of tasks?
It ranges, starts with basic file processing, then making animated GIFs.
Animated GIFs. Seriously.
Yeah. Using the image GIF package, it's a fun visual way to start. Also shows Lessage's figures, those cool, swirly patterns.
Okay. More engaging than Hello World.
Definitely. Then it moves to concurrent network clients fetching multiple web pages at once using goroutines.
Ah, showing off the concurrency early.
Exactly. And finally, setting up a very basic web server using the NethTTP package. So you get a real taste of Go's range.
And how's the code itself structured? You mentioned packages earlier.
Right. Code is organized into packages. Think libraries or modules. A package is just one or more .go files in the same directory.
And each file says what package it belongs to.
Yep. Starts with package main for an executable, or package something else for a library. Then you have import statements to bring in other packages you need.
So import is how you reuse code.
Yeah.
Like import FMT for printing.
Exactly. Or import image color. When you import something with slashes, like image color, you usually refer to its contents using just the last part. So color white.
Got it. And the tutorial covers basic syntax too.
Oh yeah. Things like fmt.println for output, for loops, including the range keyword, which is super useful for iterating.
Range for loops.
Yeah, loop over slices, arrays, maps, strings, even channels. Very versatile. Also, if statements and creating maps, key value stores using the make function.
Maps like dictionaries or hash tables.
Precisely. And it introduces pointers, too.
How does it handle those?
Shows the AND operator to get a variable's address, and the operator to dereference a pointer get the value it points to. And it points out that the default, or 0 value, for a pointer is nil, meaning it doesn't point anywhere yet.
Okay. What about defining your own types? The book mentions named types.
Right. You can use the type keyword to give a new name to an existing type. Or define a struct, like type point struct x, y, int. It helps make code clearer.
And constants. Values that don't change.
Declared with const. Their value has to be known at compile time. Numbers, strings, booleans. Simple enough.
The tutorial also introduces short variable declarations and tuple assignment. Sounds like syntax sugar.
Kind of, yeah. Useful shortcuts. The S operator lets you declare and initialize a variable in one go, and Go infers the type.
Nice.
And tuple assignment lets you assign multiple values at once, like x, y, y, x to swap variables, or handling multiple return values from functions. Very concise.
Okay, good overview of the tutorial basics. Chapters 2 and 3 go deeper into core types. Integers first, what's the story there?
Go gives you a range of integer sizes. Signed int 8 and 16 and 16 or 264 and unsigned in 64.
Signed and unsigned, different sizes. Standard stuff.
Pretty standard, yeah. Signed insters use 2's complement for negatives. You just need to pick the right size for the range of values you expect.
What about non-integers?
You've got float 32 and float 64 for floating point numbers, and even complex numbers. Complex 64 and complex 128.
Complex numbers built in.
Yep, and all the usual operators work: arithmetic plus enter, logical and inferences, comparisons, Google Register, etc. Standard operator precedence applies.
How do you write numbers literally in the code?
Yeah.
Literals, right.
Right. Decimal is normal, like 123. Octal starts with 0, like 0777. Hexadecimal starts with 0x or 0x, like 0x bad face.
0x bad face, okay.
Yeah.
Useful for bit patterns.
Exactly. Hex is great for that.
Now, strings. Fundamental for text. What's special about Go strings?
Key thing. They're immutable sequences of bytes.
Immutable means you can't change them once created.
Correct. And critically, they're typically interpreted as UTF-8 encoded text.
UTF-8 for international characters.
Yes, essential nowadays. You usually write string literals in double quotes like this.
The book mentions raw string literals too. What are those?
Those use backticks like this. The big deal is that inside backticks, escape sequences like N are not processed. They are treated literally.
So good for multi-line strings or regex.
Perfect for that. Or Windows paths with backslashes. What you type is what you get.
And those escape sequences, like N.
In double quoted strings, yeah. N is new line, T is tab, is a literal double quote, is a literal backslash. You can also use hex or octal escapes for arbitrary bytes.
You mentioned UTF-8 in Unicode. How does Go handle characters that aren't simple ASCII?
Since Go source is UTF-8 and strings are conventionally UTF-8, you can put Unicode characters directly in your string literals.
Okay.
And the Unicode F8 package helps you work with individual Unicode code points, which Go calls runes.
Runes?
Yeah. And the range loop over a string is really smart. It automatically decodes the UTF-8, giving you one rune at a time, even if a rune takes multiple bytes.
So range handles the complexity of multi-byte characters.
Exactly. You get the starting byte index and the rune itself. Very convenient. If you just use len, you get the number of bytes, not runes.
Right. How about manipulating strings, getting parts, joining them?
You can get a substring or slice using start.end notation. Omitting start means from the beginning, omitting end means to the end.
Like Python slicing.
Very similar, yeah. And you join strings with the plus operator. S1 plus S2 creates a new string, remember, immutable.
What about converting between number types, like into float?
Go is strict here. No implicit conversions. You must do it explicitly. Float 64, my height, or int my float.
Why so strict?
Prevents accidental data loss or unexpected behavior. When you convert float to int, the fractional part is just dropped truncated towards 0.
Good to know. And converting a number too big for the target type.
That's implementation dependent, the book warns. Could be unpredictable. Best avoided.
Okay. Lastly on basics, constants have a flavor. What's that about?
Right, untyped constants.
Yeah.
A literal, like 123 is an untyped integer constant. 3.14 is an untyped float constant.
Untyped.
Yeah, they don't have a fixed Go type like int32 or float 64 yet. They're more flexible. You can assign 123 to an int, an ins8, or an ins64 variable without explicit conversion as long as it fits.
Ah, the compiler figures it out.
Kind of. It has a default type it uses if needed, like
Yeah.
int for 123, float 64 for 3.14, but it keeps them flexible as long as possible.
Interesting. Okay, that covers the basics. Chapter 4 moves to composite types grouping data. Arrays first.
Arrays in Go are fixed length sequences. All elements must be the same type.
Just length.
Yep. And the length is part of the type. So 3int is the different type from 4int. The size has to be known at compile time.
And how do you initialize them?
With an array literal, like 3int123. Or you can let the compiler count using Pliny1, like .ant1234. That makes a 4int. You can also initialize specific indices, 5, I, and 10, 4, 50. Unspecified elements get the 0 value.
0 value like 0 for ints, false for bools.
Exactly. For strings, nil for pointers, etc.
Okay, but slices sound more common, more flexible.
Oh, absolutely. Slices are fundamental in Go. They are dynamically sized views into an underlying array, much more common than raw arrays.
A view into an array, how does that work?
A slice has 3 parts, conceptually. A pointer to the start of its segment in the underlying array, a length, how many elements it currently contains, and a capacity, how many elements the underlying array has from the start of the slice to the end of the array.
Length and capacity. Okay, how do you make slices?
You can use a slice literal, like in 123, note the missing length, or you can slice an existing array or slice.
MyArray 1.4.
With the string slicing, very similar. And the built-in make function is common. Make, int 5, creates a slice of length 5, capacity 5. Make, int 0, 10, creates a slice of length 0, capacity 10.
What about adding elements? The book mentions append.
Right, append is the built-in function to add elements to the end of a slice. My slice, append. My slice, 4, 5.
Boy, the assignment back to my slice.
Because if the underlying array didn't have enough capacity, append might need to allocate a new, larger array, copy the old elements over, and add the new ones. So the slice itself, its pointer, length, capacity might change. Append returns this potentially new slice.
Ah, so the underlying array might change.
Right.
Got it. And copy.
Copy just copies elements from a source slice to a destination slice.
Yeah.
Copy DS, DSRC. It copies up to the minimum of their lengths. Useful for bulk copying.
Okay. Next up, maps. Key value stores.
Yep. Goes built-in hash tables or dictionaries. Super useful. You map keys to values.
What kind of keys and values?
Values can be anything. Keys can be any type that's comparable, meaning you can use on them. So numbers, strings, booleans, pointers, structs, if their fields are comparable. Not slices or maps themselves, though.
How do you create a map?
Usually with make. MyMap, make, stringent app, creates an empty map where keys are strings and values are integers. You access elements like MyMap key, one or value, MyMap key.
Okay. And structs, grouping different types together.
Exactly. Aggregate types. You define a struct with named fields, type person struct, name string.
And creating instances.
You struct literals, either positional person, Alice, 30, or named person name, Bob, age 42. You access fields with dot notation, pname, ph.
The book mentioned embedded fields again here, remind me.
Yeah. If you include a type in a struct without giving it an explicit field name, it's embedded.
Like type employee struct, salary float 64.
Exactly. Then an employee automatically gets the name and age fields from person. You can access them directly. Ename.
And it gets the methods, too. Method promotion.
Yes, that's the powerful part. If person had methods, you could call them directly on the employee variable, person method. It's Go's way of doing composition feels a bit like inheritance sometimes.
Cool. Now, JSON, super common for data exchange.
Yeah.
How's Go with JSON?
Excellent built-in support in the encoding JSON package.
How does it work?
Two main functions. JSON. Marshall takes a Go value, like a struct or slice, and turns it into JSON bytes.
Encoding.
Right. And JSON. Unmarshall takes JSON bytes and decodes them into a Go variable you provide a pointer to.
Decoding. Does it map JSON keys to struct fields?
Yes, usually by matching names, ignoring case. But you can customize it using struct tags.
Struct tags, what are those?
Little strings and backticks after a field declaration. Name, string JSON, full name. This tells the JSON package to use full name as the key in the JSON, not name. You can also use tags like omit empty or to skip fields.
Very flexible. The book shows hitting the GitHub API.
Yeah, a nice real-world example, fetching JSON issues and unmarshalling them into Go structs.
And for outputting formatted text, there are templates.
Yes, the text template package and HTML template for HTML. You write a template string with placeholders like dem name, and then execute it with a data structure, like a struct.
Placeholders get filled in.
Right. It supports conditions, loops, calling functions, and even pipelines. Data process one process where output flows into the next step, like Unix pipes. Good for reports, emails, config files.
Okay, powerful stuff. Let's move to chapter 5. Functions. The core building block, declaring them.
Starts with func, then the name, parameters in parentheses, name type, optional results also in parentheses, type 1, type 2, and the body in curly braces.
Optional results.
Yeah. If you have one unnamed result or no results, you can omit the parentheses around the result list. Just func, myfunc, or funcdeuce, or something.
Can functions return multiple values?
Yes, absolutely. Very common in Go. Often used to return a result and an error status.
The error handling pattern. How does that work typically?
The convention is, if a function can fail, it returns an error value as its last return value.
What is an error?
It's a built-in interface type. Any type that has an error string method satisfies this interface. So functions return their normal results, plus potentially an error. The caller checks if the error is nil or not.
So no exceptions like try-catch.
Generally, no. Go prefers explicit error checking via return values. The idea is it keeps control flow clearer. You handle the error right where it occurs.
Okay. Functions are also first-class values. What does that mean?
It means you can treat functions like any other data type. Assign them to variables.
Myfunc, end function.
Exactly. Pass them as arguments to other functions. Return them from functions. Store them in data structures.
Very flexible.
Extremely. The zero value for a function type variable is nil. Calling a nil function causes a panic.
What about anonymous functions? Closures.
Go supports literals functions without a name, often used inline.
Like lambdas.
A similar idea, yeah. And they are closures, meaning they can access and use variables from the surrounding scope where they are defined.
Even after the outer function returns.
Yes, they close over those variables, retaining access. Very useful for callbacks, routines, defer statements.
The book mentioned a pitfall with closures and loops. Capturing loop variables.
Yes, the classic. Gotcha. If you create closures inside a loop and they refer to the loop variable, like the index one, they all capture a reference to the same variable.
So they all see the last value of I.
Often, yes, if they run after the loop finishes. The fix is usually to create a copy of the loop variable inside the loop body for each iteration and have the closure capture that copy.
Good tip. What about the defer statement?
Defer schedules a function call to be executed just before the surrounding function returns.
For cleanup.
Exactly. Perfect for closing files, unlocking mutexes, releasing resources. Ensures cleanup happens regardless of how the function exits normal return or panic. Multiple defers run in LIFO order, last in, first out.
LIFO, okay. And panic and recover. Sounds like exception handling light.
Sort of. Panic is for truly unexpected, unrecoverable errors, usually programming bugs. It stops normal execution in the current Go routine, runs deferred functions, prints a stack trace, and crashes the program.
So use sparingly.
Definitely. Recover is a function you can call inside a deferred function to regain control after a panic. It stops the panicking sequence and returns the value passed to panic. But again, the Go philosophy discourages using panic recover for normal error handling. Use error values for that.
Got it. Use errors for expected problems. Panic for disasters. Chapter 6 moves to methods. How are they different from functions?
Methods are functions associated with a specific type called the receiver.
For the receiver, like this or self.
Exactly. You declare it in parentheses before the function name. Func p point distance, float 64. Here, p is the receiver of type point.
How do you call a method?
Using dot notation on a value of the receiver type, my point distance.
Can methods change the receiver value? Like modify the point?
Yes, if the receiver is a pointer, 6-diners, scale by, factor float 64. This method receives a pointer to a point and can modify the original point value it points to.
Value receiver versus pointer receiver. Important distinction.
Very. Value receivers operate on a copy, pointer receivers operate on the original.
And method promotion with embedded structs applies here too.
Yes. If you embed point in another struct, say colored point, then methods of point, like distance, can be called directly on a colored point variable. myColoredPoint.distance.
Nice way to reuse code. What are method expressions?
They let you treat a method like a regular function value. If point has distance, then point distance is a function value.
What's its signature?
It takes the receiver as the first argument. So point distance would be like func point float 64. If it was a pointer receiver method, point. Scale by, the expression, point. Scale by gives func point float 64, useful for passing methods around.
Okay. Finally, for methods, encapsulation. How does Go hide implementation details?
It's super simple. Capitalization.
Just upper versus lowercase.
Yep. If an identifier, type name, function name, method name, field name, variable name, constant name, starts with an uppercase letter, it's exported visible outside the package. If it starts with lowercase, it's unexported private to the package.
So the package is the boundary.
Exactly, not the struct or type. Anything within the same package can access each other's unexported members. To encapsulate, you typically make struct fields lowercase and provide uppercase methods to interact with them.
Simple but effective.
Okay.
Chapter 7. Interfaces. Key concept. What's the Go take?
An interface type defines a set of method signatures. Type reader interface, read NEP byte, PI ind, error.
Just the signatures, no implementation.
Correct. It's a contract. Any concrete type, like a struct, that implements all the methods specified in the interface automatically satisfies that interface.
Automatically. No implements keyword like Java.
No implements keyword needed. This is huge. It's called implicit interface satisfaction or structural typing. If a type looks like it fulfills the contract, has the right methods, it does.
That sounds really flexible, decouples things.
Yeah, massively. You can define an interface based on the behavior you need, and any type that provides that behavior, regardless of where it came from or its other methods, can be used where that interface is expected.
So what does an interface variable hold?
Conceptually, two things. A dynamic type, the actual concrete type of the value stored inside, and a dynamic value, the value itself.
Dynamic type and dynamic value.
Right. An interface variable is nil only if both are nil. If you have an interface variable holding, say, a non-nil pointer to a struct, the interface value itself is not nil. Calling a method on a truly nil interface value panics.
How do you get a value into an interface variable?
Just assign a value of a concrete type that satisfies the interface. Var io reader equals ostin. This works because os.file, the type of ostin, has the required read method. The interface value now holds the dynamic type os.file and the dynamic value of ostarted.
Okay. The book mentions standard library interfaces. Sort.interface.
Yeah, that's the contract for sorting. Requires 3 methods. Len, number of elements, less ei, et bool, is element I less than element j, and swap I jit, swap elements I and j.
So you implement those 3 on your collection type.
And then you can use sort to sort it. The sort package also has helpers like sort ins, sort strings for common slice types.
What about HTTP.handler for web servers?
Central to Go web programming, it has just one method. Serve HTTP, response writer, request. Any type implementing this can handle HTTP requests. You pass your handler to the web server, very modular.
And the error interface again?
Yep. Just one method. Oh, error, string. Returns a description of the error. So simple yet so powerful. Any type with that method is an error. Makes error handling consistent.
How do you get the original type back out of an interface if you need specific methods?
Use a type assertion.value OK. My interface var concrete type. It checks if the interface holds that specific concrete type. If yes, OK is true, and value gets the underlying value typed as concrete type. If not, OK is false.
The OK prevents a panic if the type is wrong.
Exactly. There's also a form without OK that panics on failure. And for checking against multiple types, use a type switch.
Type switch.
Looks like switch v, my interface var.type case type 1, case type 2 default. It lets you branch based on the actual concrete type held by the interface.
Very useful. Okay, chapters 8 and 9. Concurrency. Go superpower. Let's start with goroutines again.
Lightweight concurrent functions. You start one with the go keyword, go my function. Much cheaper than OS threads.
How do you wait for them to finish?
A common way is sync, wait group. You add one for each goroutine you start, have each goroutine called defer WG done before it finishes, and the main goroutine calls WG wait to block until the counter hits 0.
Wait group. Okay. And communication, channels.
Channels are typed conduits for sending and receiving data between goroutines. CH, rage, make, chan, and teat. Send with Jan Azeo, receive with value.
Synchronized communication.
By default, yes. Unbuffered channels, made with just make, require both sender and receiver to be ready at the same time. One blocks until the other arrives. This provides synchronization.
What about buffered channels?
You give them a capacity, make, changti 10. Senders only block if the buffer is full, receivers only block if it's empty. More like a queue, less strict synchronization.
Need to watch out for deadlocks.
Yeah.
Goroutines waiting on each other forever.
Absolutely, a classic concurrency problem. Go detects simple deadlocks at runtime, but complex ones are possible. You can also close a channel to signal no more values will be sent. Receivers can check for closure.
And the range loop works on channels.
Yep. For value, it receives values until the channel is closed. Very clean way to process results from a worker goroutine.
What's the select statement for?
Multiplexing. It lets a goroutine wait on multiple channel operations, sends or receives at once.
Like waiting for the first message from several channels.
Exactly. Select case V, manage H1, case 2, manage X. It waits until one case is ready, then executes that case. If multiple are ready, it picks one pseudo-randomly.
What if none are ready?
It blocks, unless you have a default case. Selected default do something non-blocking. The default runs immediately if no other case is ready. Select is key for timeouts, time after, cancellation patterns, done channels, and non-blocking ops.
Concurrency often leads to race conditions, accessing shared data unsafely.
Right, when the outcome depends on the unpredictable timing of goroutines accessing shared variables. Big source of bugs.
Does Go help find these?
Yes. Go has a built-in race detector. Compile and run with the docs race flag. Go run -racemain.go. It instruments the code and reports potential data races at runtime. Incredibly useful.
How do you prevent races?
Synchronization. The most common way is using mutexes from the sync package. Sync mutex. You lock it before accessing shared data and unlock it afterwards, often using defermux unlock. Only one goroutine can hold the lock at a time.
What about lots of readers, few writers?
Use synced on RWMutex. It allows multiple goroutines to hold a read lock simultaneously, rlock or unlock, but a write lock, lock and lock, requires exclusive access, better performance for read-heavy workloads.
The book uses memoization as an example.
Yeah, caching function results. Shows how a naive concurrent cache has race conditions, and then how to fix it using both a mutex and a channel-based approach. Good illustration.
What about the Go scheduler and OS threads? GOX Pro CS.
The Go runtime has its own scheduler that multiplexes potentially many goroutines onto a smaller pool of OS threads. GeoMax Pro CS sets the maximum number of OS threads that can be executing Go code simultaneously. Defaults usually to the number of CPU cores.
So Go manages the mapping of goroutines to threads.
Yes, efficiently. You usually don't need to tune GeoMax Pro CS unless you have specific performance needs for CPU-bound work.
Okay, solid overview of concurrency. Chapters 10 and 11, packages and tools, essential stuff. Workspaces, and the Go tool.
The Go command is your main interface. Go build, go run, go test, go get, or dependencies, go FMT for formatting. It relies on a workspace structure, historically GeoPath, now more commonly Go modules, to find packages.
Package import paths, how do they work?
They're unique strings identifying a package. Standard library ones are simple, FMT, NFTTP. Third-party ones usually look like URLs. github.com/jin-gonogen. Tells the Go tool where to find the source.
Package names, conventions.
Should be short, lowercase, descriptive, usually the last part of the import path. Package HTTP and METHPTP. Exceptions, package main for executables, package footist for test files.
What about import statements? Any tricks? Blank imports.
You list imports at the top. Import, FMT math. A blank import, github.com CEPQ imports a package just for its initialization side effects, like registering a database driver, but you don't use its names directly. The underscore signals this.
Naming advice for packages and members. Exported versus unexported.
Keep package names clear. Exported names, start with uppercase, are the public API. Unexported lowercase are internal details. Think about what users of your package need to see. Sometimes a package exports mainly one type, like template, sometimes many related things, NFTTP.
How to organize code. One package per directory.
Yes, that's the rule. One package per directory. For projects with executables, a common layout is a CMD directory containing subdirectories for each main package. Library packages live elsewhere in the project structure.
Building code. Go build.
Yep. Go build in a main package directory creates an executable. In a library directory, it compiles the package but doesn't output anything directly. The result is usually cached.
Documentation. How important is that in Go?
Very. Godoc is built in. You write doc comments right before package declarations, types, functions, etc.
Doc comments.
Just regular comments or immediately preceding the thing they document. Package comments often go in a dedicated doc.go file. Godoc fmt.println shows you the docs.
Chapter 11 focuses on testing.gotest.
The standard tool. You write test files ending in test.go in the same package directory. They aren't part of the normal build.
What goes in these files?
Test functions, testxxd, testingd, benchmark functions, benchmark_xxb, and example functions, example.xx, test functions, testing.t. Right. Itman.us is your handle for reporting failures. T-error, MSG, T-error format args, or T-fatal-fatehaf if the test can't continue after the failure. GoTest runs all testxx functions and reports results.
What are test tables?
A pattern for organizing tests. Define a slice of structs where each struct holds inputs and expected outputs for one test case. Then loop over the table in your test function. Keeps tests DRY and easy to extend.
Black box versus white box testing.
Black box tests only use the package's exported API. White box tests might access unexported stuff, possible if the test is in the same package, or using special techniques because they know about the internals. Both are useful.
Any setup teardown support?
Not explicitly built in like if some frameworks, JNet, PyTest fixtures. You typically use standard Go. Helper functions, package level setup if needed, and defer within test functions is great for cleanup.
Advice for writing good tests.
Keep them focused. Clear error messages, avoid brittleness, don't rely on irrelevant implementation details. Test behavior, not just internal state.
Coverage. Does Go measure test coverage?
Yes, GoTest -in cover shows percentage coverage. GoTest -cover profile, coverage -out generates a profile you can analyze with Go tool cover -HTML coverage dart out to see exactly which lines are covered. Useful, but don't chase 100% blindly. Meaningful tests matter more.
Benchmarks for performance.
Yep. Func. Benchmark XXXB testing B. Inside, you loop BN times running the code you want to measure. GoTest-bench runs benchmarks. BN is adjusted automatically to get statistically stable results.
Profiling, finding bottlenecks.
Also built in GoTest-cpu.prof or GoTest-memprofile mem.prof. These generate profile files you analyze with GoToolProf. It's incredibly powerful for understanding CPU usage and memory allocation hotspots.
Great tooling. Chapter 12. Reflection. Inspecting code at runtime.
Exactly. The reflect package lets a program examine its own structure types, values. Reflect, type of X gives the type, reflect val X gives the value.
Why would you need this?
Writing generic code that works with many types. Examples. Generic formatting functions, serialization libraries like encoding JSON uses it heavily, dependency injection frameworks, ORMs, the params. Unpack example in the book populates a struct from HTTP parameters using reflection and struct tags.
Sounds powerful, but maybe complex? Any pitfalls? Cycles?
Definitely can be complex. And yes, if you're recursively traversing data structures with reflection, you need to handle cycles where A points to B, which points back to A, carefully to avoid infinite loops. Requires keeping track of visited objects.
Okay. Final topic, Chapter 13. Low-level programming, unsafe and SCO. Sounds scary.
It should be used with extreme caution. The unsafe package bypasses Go's type safety, very rarely needed, can cause crashes and subtle bugs.
What does it let you do?
Get memory layout info, unsafe, size and bytes, unsafe, alignment off T, alignment requirement, unsafe, offset of struct field, offset with instruct, useful maybe for optimization or interrupt.
And unsafe? Pointer.
It's a generic pointer type, like void in C. You can convert between regular pointers, T, unsafe, pointer, and int PTR, an integer type holding an address. This allows pointer arithmetic. Very dangerous. Relies on implementation details.
Mighty dangerous.
The garbage collector can move things in memory. Pointer arithmetic can easily lead to invalid memory access. The book shows a deep equality check using it, but emphasizes the risks.
What about CGO? Calling C code.
CGO lets go, code call C code, and vice versa. You embed C code in special comments, import the C pseudo package. CGO handles the bridge.
Useful for reusing existing C libraries.
Yes, but there's overhead in the calls, and you have to be careful managing memory across the GOC boundary. Again, use only when necessary.
Final warnings on unsafe and CGO.
Use extremely sparingly. Don't rely on memory addresses staying fixed. They interact poorly with the GC if misused. Stick to safe Go unless you have a very compelling reason and understand the deep implications.
Right. Well, that was an incredibly thorough run-through of the Go language based on these book excerpts. If we try to boil it all down, what are the absolute key takeaways, a core philosophy?
I think it boils down to simplicity, efficiency, and robust concurrency support. It's got this clean syntax, it compiles fast, runs fast.
Yeah.
And the way coroutines and channels are built in makes concurrent programming feel, well, much more natural than in many other languages.
And that deliberate minimalism we talked about.
Yeah, the focus on a smaller set of orthogonal features, leaving things out to keep the language stable and easier to learn and reason about, strong typing, explicit error handling, it all aims for clarity and reliability.
So how do these things help developers build better software? What's the practical benefit?
Well, the simplicity means faster learning, easier reading, and maintenance. Productivity boost, maybe?
Makes sense.
Efficiency means faster builds, better performance, using resources well. Concurrency means building scalable systems that use modern hardware effectively. Explicit errors mean fewer surprises, hopefully more robust code.
So a pragmatic approach aimed at building solid, modern systems.
I think that's a fair summary, yeah.
Okay, a final thought then for you, the learner. As you think about Go, consider how its design choices that focus on simplicity, the specific concurrency model, the explicit error handling, how might those ideas influence how you think about solving problems or designing software, even if you're using a completely different language? It's worth pondering.
Definitely. The Go way might offer perspectives applicable elsewhere.
Absolutely. We really encourage you to dive deeper into Go and its ecosystem based on what we've covered today. Thanks for joining us on this deep dive, and if you have other sources you want us to explore, please do send them our way.